Alright, this is Chapter 4, Ionic Compounds, Formulas, and Reactions. This is Matt with Peervids again, doing AP Chem Barron's book. So, it's an important chapter. Doesn't look like there's too much math, but there is a lot of important basic stuff that you're really going to have to learn. Alright, well, this is going to be my first example of a compound, of an ionic compound. It is aluminum nitrate. And it is gonna just show us a couple things about writing compounds. First, very basic, I'm sure all of you know it, but I should cover it anyways. When you write compounds, you use the abbreviation or the symbol of the element. So, aluminum, this is Al, and then N, nitrogen, O, oxygen. Now, you're probably wondering why NO3 is in a parenthesis. NO3 is in these little parentheses because they NO3 makes a polyatomic ion. If you're in advanced chemistry, you probably have a nice periodic table with a table of common polyatomic ions. If you do not have this table, you can find it probably online, maybe even in the Barron's book. It's very similar to the one you will be given on the AP test, but I don't think they give you one for some of the sections. I don't remember everything. But anyways, so that makes the polyatomic ion of nitrate, which is NO3. So that's 1 nitrogen and 3 oxygen. Now, there's also this little 3 right here. That means there's 3 nitrates attached to the 1 aluminum. So when you do a total tally of every element that you have here, you have 1 atom of aluminum, 3 atoms of nitrogen, and 9 atoms of oxygen, because 3 times 3 makes 9. So those are a couple key takeaways. Another thing you can do is, if you look on probably your table, or once you learn your charges a little better of basic ones, you'll see that aluminum as an ion comes in 3+. Well, nitrate, NO3, comes in 1-. So, to even this out, and so you can make the ionic bond, you need 3 minuses, right, to cancel the 3 pluses, and that's why you get 3 nitrates, because that will make 3 minuses, which will go with the 3+ on the aluminum. Later, that's just a simple way to look at it, cancel out charges, but later you'll have to learn which how each thing bonds with each other electron, like valence electrons and how they combine. But for now, simple, easy, and it works. Alright, so here is another form of compounds that you will see written. This is a hydrate, so this means that the compound has a fixed number of water molecules and its lattice structure. So the first thing we're going to look at is the cobalt. This is cobalt chloride. Now again, when you look on the table, you see cobalt comes in 2+ and 3+. So there's 2 common ions. Well, since there's only 2 chlorine atoms on it, you know that this is cobalt 2+, because chlorine has a 1 negative charge, because it is a halogen. So if they did ask you to split this up in a sort of chemical reaction, you would know that this is cobalt 2+, because of the amount of chlorine. Now we're going to look over here. There's 6 water molecules. So when we name this, this is the hexahydrate of man, how's that spelled? Hexahydrate. Oh, it's awful. Alright, I'm going to try that again. It's the hexahydrate of cobalt chloride. So you can write that as cobalt chloride hexahydrate. Naming or nomenclature, very important in chemistry, because especially like organic chemistry, you're going to have to be able to read names and determine exactly what each molecule is just by the name. So it also ties into common polyatomic ions. Those are a huge part of names, and then later when you learn ligands. That's much later though. So here, just a brief slide. This is the prefixes used for hydrates. So there's one hydrate, it's a monohydrate, two dihydrate, three trihydrate, and so on. Prefixes also very important in the nomenclature, and some of them, this will probably bother you, some of them use different different things. So for those, first couple especially, usually the later ones stay the same, but like when you're doing organic chemistry, you get butanol, and that's the butyl is going to be the prefix for 4, and then you get propanol, and the propyl is the prefix for 3. It's really just methanol, yeah. So it's really kind of weird, but each section seems to have its own prefixes, but there's a good amount of overlap. So just make sure you learn which prefix goes with which section of chemistry, because very important in naming. Alright, so here's a pretty basic chemical reaction. It's a combustion reaction, which is another thing you guys need to learn about. So combustion reactions, when you get nice hydrocarbon, like for here I have methane. Don't worry about the naming of this, it's going to come up in organic chemistry later, but it's methane, which is CH4, and so a hydrocarbon plus a certain amount of oxygen will yield carbon dioxide and H2O, which is water. Usually this will all be on one line, but spacing, I just did it on 2, and I use different colors for the products and the reactants. So this section over here, these are reactants. They're reacting together to yield a product. And that guy right there, that's the yield sign. So we're going to balance this chemical reaction. Well, it's going to happen in a couple steps. So first, let's just assume there's like it's another color. Can you, yeah, I'll try yellow. Alright, so there's one molecule of methane. Methane's really easy because there's only one carbon and 4 H's. Makes a very nice for us to do a simple reaction. Later you might get like methanol, and it's going to be CH3OH, and that like extra oxygen will make you have to have like 2 or more of that molecule to make it balance, and it's a little ugly, but for now we just have methane. So 1 molecule of methane. We don't know how much oxygen yet, so we're going to leave that. Now we're going to go over here. 1 carbon that on the reactant side. So if we have 1 carbon on the reactant side, it means we need another carbon over here. So there's going to be 1 carbon. Now, if we have 1 carbon in our CO2, that means we have at least 2 oxygen. Well, we also see that there's 4 hydrogen in this 1 methane. So that means there's 2 hydrogen per water molecule. So that means we need 2 water molecules, because 2 times 2 would make 4 hydrogens total. So we see from the 2 oxygen here and the 2 times 1 there, so that makes another 2. So we get 2 plus 2 equals 4 oxygen atoms, but that's oxygen by itself. O2 on this side is it's a molecule, right? So we only need a 2 there, because 2 times 2 makes 4 of the single. So 2, 2, that would make the 4 right there. So our final balanced equation will be 1 CH4 plus 2 O2 yields 1 carbon dioxide molecule plus 2 water molecules. Now, normally when you balance an equation, you'll leave these 1's as empty, just like when you do algebra, you don't write 1x. It's just an implied 1, but just to help you visualize better, I put the 1's in. So that's balancing equations. Alright, so here's another example of balancing equations with a harder molecule. This is propane, which you can tell from 3 carbons, but again, you don't need to learn the naming of this guy, propane, until you do chem, so don't even worry about it. But so we see, again, that this has 3 carbons, so that means there's probably going to be, well, there has to be 3 CO2. So 3 CO2, that means 6 oxygen, right? 3 times 2 makes 6. You get 6O there. And then, well, how many hydrogens do we have? We have 3 plus 2 plus 3, 8 hydrogens. So, and there's 2 per water molecule. So how many water molecules are we going to have? 4. Because 4 times 2 makes 8. So, how many oxygens do we get from this water molecule? 4 times 1 makes 4. So 6 plus 4 makes 10. Pretty easy math right there. So how many oxygen molecules does that mean we have? There's 2 oxygen per oxygen molecule. We're going to have 5 oxygen. Because that way, with balances, we get 10 oxygen there, and we get 10 oxygen there. We get 8 hydrogen here, 8 hydrogen there, and we get 3 carbon on each side. So this equation is balanced at 1 molecule of propane plus 5 oxygen molecules makes 3 molecules of carbon dioxide and 4 molecules of water. So here is a list of most, if not all, of the reactions you'll see in your year of chemistry. We have combustion, single replacement, double replacement, neutralization, synthesis, formation, addition, decomposition, net ionic, half reaction, oxidization, reduction, or redox, and nuclear. So I could show you examples of all of these, but there would be no real point because you wouldn't learn much, and it would just be a bunch of busy work where you're just kind of floating through balancing. But you will see all of these throughout the year, and you will need to know what each reaction is called. So you just get a jump on it. The ones you'll probably see first are combustion, single replacement, and then once you start decomposition, nuclear, and once you start the organic chemistry, which for me was first semester, you'll get some formation, synthesis, neutralization is acid-base, redox is redox, and net ionic you'll see too. That's just a way to write equations. But for now, we're just going to leave it at names, and then I'll explain each type again when they come up later. If you need more detail now, the Barron's book has like 3 or 4 pages just explaining a little bit of each of these reactions, but I don't think it's important to know now. Alright, well, there's 2 main types of bonding that you will talk about in your chemistry year, especially at the start. You're going to talk about covalent and ionic bonds. Well, covalent bonds are when 2 or more atoms share valence electrons to form a bond. So you get this when say 2 hydrogen, for example, because they're easy. Each one has 1 valence, right? Well, the stable state in the first row is to have 2 electrons in that shell. So these 2 will share their 1 electron each, and they can have nice little 2, and then they get a little back going where they both orbit both. And they get 2 electrons in their, it's probably not a super accurate drawing, but it's the way I like to think of it. So each one gets 2 electrons orbiting their nucleus, making hydrogen gas, H2. and that's why it's so common, because it's more stable than just single hydrogen atoms. Alright, well, ionic bond is when there's an attraction between ions to form a compound. So that's like when we saw aluminum nitrate. So I'm going to put attraction between ions. So if you remember, we had the aluminum 3+. It's got a positive charge, right? And we had, it's not where I want that, 3. And we have 3 NO3, and they each had a minus, right? Well, these minuses, they're attracted to each other, the minus and the plus, because like magnets, opposites attract. So they attract to each other and then they bond. They make a strong bond, and then the aluminum gets the extra electrons from the nitrate, and it's written, if I can fit this on the screen, Al. Then you'd have nitrate. I can't fit this on the screen. That's alright, it's not too important, but how it's written right now. But that's the basic idea behind the ionic versus covalent. The covalent, again, shares the electrons to form a bond, whereas the ionic, there's an attraction between the ions, and that makes the bond. The next thing your book talks about is the S and P orbitals, or the electron configurations of noble gases. I'm not going to go too much into this because I went over this already. So this is like helium, for example. This is 1s2. Neon is a 1s2, 2s2, 2p6. Remember, but it's a noble gas, so all its shells are filled completely. So you will have full shells. And another way you can check, neon's number 10 has 10 electrons, then 2 plus 2 plus 6 makes 10. Whereas helium, second, should only have 2, and it has 2. Alright, the book has a brief little blurb on ionic substances here, so I feel like I should just put that in. Also, brief little blurb. The things that are negatively charged ions, like for example we had NO3 minus, these are called anions. These are usually these are the columns after the metals or the transition elements. This is they're all nonmetals. This is nitrogen, phosphorus, arsenic, oxygen, sulfur. Just atoms like that. They make cations because they gain electrons. Well, on the other side, like elements like lithium and magnesium, just the ones that get positive charge, they lose electrons and they become cations with positive charges. So, and they are attracted to each other. Certain elements are more prone to do this than others, so that's why we have this table of common polyatomic ions. Not sure what your teacher will want you to do, but my teacher had us memorize this table going into second semester because you use it for everything. And now, thinking on it, I don't think they gave it to you on the test. So, start working on that Christmas time-ish over break, unless your teacher tells you to do it sooner. Very important. Alright, the next relevant thing in the Barron's book is polyatomic ions. I talked about them. I didn't really explain them very well, or at all. The polyatomic ions are, well, if you can figure out the name, it's exactly what it sounds like. Poly, many, atomic, atoms, ions, means charges, right? So you get this table of common polyatomic ions, and you just get a bunch of ions that are made up of more than one element, so, or more than one atom. So most ions, or I shouldn't say most, just a lot of ions are standalone things. Like you get O2 minus, and that can be by itself. You get fluorine minus. Those are standalone ions. Well, the common polyatomic ions, they're just atoms that come together but still have charges. They're still ions. So, like ClO4 minus, it's a chlorine with 4 oxygens on it, but it still has a negative charge. So, it's a polyatomic ion. It's got more than one atom. And there's just a bunch of these. There's, like, my table probably has, like, close to 20 or 30 on it just by itself. And that's just, like, really common ones. But, yeah, and there's some weird naming rules you're going to have to learn. Nomenclature. Like, nitrate is NO3 minus, and nitrite is NO2 minus. And it's a mess, but they're important. Alright, well, luckily, when we're doing some naming now of naming ionic compounds, it's very easy. You just take the name of the cation, and then you tack on the name of the anion. Very simple. So, it's even written out the same way in your formulas, usually. So, for example, that is calcium with 2 nitrates. Well, that makes calcium nitrate. Calcium is the cation because it's 2 electrons short, loses 2 or 3 depending on the calcium, but or only 2. Sorry, I'm thinking of chromium. It loses 2 and it makes it a anion with a positive charge. It meets up with 2 nitrates that are anions with negative charges, and then they bond. And calcium nitrate. Very easy. Another one, well, NH4. NH4 plus is a polyatomic cation. We put 2 of those with sulfate, if I remember correctly. And I do. That is sulfate. Now, sulfate is a polyatomic anion with a 2 minus charge. That's why there's 2 of ammonium, which is a positive polyatomic cation with a +1 charge. Well, how do we name it? Very simple. Ammonium sulfate. Therefore, the name is ammonium sulfate. You're probably like, why is it named ammonium? That's the name it's given on the polyatomic ion table. Why is it named sulfate? It's the name on the polyatomic ions chart also. So, just take the 2 names from the chart or from just the name of the single ones. Unfortunately, the single ones tend to be a little different. I'll cover that in the next slide. Alright, well, when you're just using single anions and versus polyatomic ions, you don't use the ite or the ate. You use a IDE ending on the end of their element. So, for example, KCl, that's potassium with chlorine. Potassium is the cat ion, chlorine anion, and it is potassium chloride. So, it's a little more nomenclature for you. It's a little weird, but again, nomenclature, very important. If there's just, if it's a single elements, or, single elements, ions, then just use the IDE rule. And if it's a polyatomic ion, just use the names of the ions. Alright, well, the next thing we have in the Barron's book is ions and solutions. You'll learn a lot more about this when you do acid-base unit, or when you do when you learn the solubility table, which Another thing you should memorize before you take the AP, because I also do not think they give this to you for most, if not all, of the test. And there are questions about the solubility of some things, but the big one that comes up a lot is, I'll probably repeat this later when we do acids, bases, and solubility, but just a hint right now is like silver chloride, AgCl. There's a couple other common ones that aren't soluble that come up a lot. But anyways, back to this. So you'll see these parentheses in reactions or equations, and you need to know what they mean. So these parentheses, they're the states of matter of the elements involved, or the atoms. So normally, I know what you're thinking. There's solid, liquid, gas. Those are all true. Also, these are usually written in subscript, but that's hard to do on this. But anyways, so solid, liquid, gas, right, that's accurate. But what could aqueous mean? Well, this is supposing that sodium bromide is dissolved in water, probably, for example. So when it dissolves in water, the ions dissociate, they separate from one another because the polarity of the water pulls them apart. It's probably more detailed than you know at this moment, but anyways, when this happens, you need to show this in your equation. So you write AQ in the parentheses for aqueous, showing that the ion is in water, and that's why. So that's just a little more rules. I know, lots of rules this chapter. Well, there's just only gonna be more. Alright, the reaction we're about to learn about is called double replacement. I briefly mentioned this in your list. It came up sooner than I thought it would in the Barron's book. So this is also to help predict products. So if they give you this equation, silver nitrate plus sodium chromate. Again, this is referring to the Polyatomic Ions table, if you do not know it. I, on the other hand, have most of these still memorized, so I'm just going from memory, but that's something you should learn so you can do naming. And these will make, well, it's called dual replacement for a reason. These, it's going to replace that with that on these ions. It's kind of weird to wrap your head around, but imagine the two anions, the nitrate and the chromate, stand still, and the silver and the sodium, they just switch places. They unhook from their partners, or their partner ion, and they just switch places. So this is going to make silver chromate plus sodium nitrate. Well, where's the second silver come from? Now we have to balance this, right? Well, there's only one silver here. Well, that means there needs to be two silver here, and then there's two silver. That makes that works. That makes these two work, because one silver times two makes two silver. Now, there was two sodium here before, right? Well, there's only one sodium here, and this gave you a second nitrate when you add this 2. So what we're going to do is we're going to make you 2NaNO3. Well, that solves that now too, doesn't it? Now this equation is balanced. There's 2 sodium on each side, there's 2 nitrates on each side, 2 silver on each side, and 1 chromate on each side. So, double replacement, not too hard if you have practiced with other ones, but when you see this set up and it just looks like 2 ionic compounds that shouldn't react, but they do, it is probably double replacement, and you can switch the cations and then balance. So that's a good way to predict products. The book touches here on something I never learned, but I guess it's kind of handy. So you've seen through the double reactions that it's pretty easy to predict the products of two ionic compounds. Well, however, not all the mixtures of ionic compounds react. So chemists or people that are solving these equations rely on a couple factors that will tell you that they're reacting. So they call them driving forces in this book. The first one, that is in the laser pen. First one, H2O product. If water is forming, there's probably a double replacement reaction occurring. The next one is formation of a precipitate. So a precipitate is when two aqueous or liquid solutions react and it forms a product that is solid. Now, to determine when this happens, you're going to look on your solubility table. If you don't have one on your periodic table on the back, there's probably one in your chemistry textbook or one online, and it'll just have a list of what ions on the top, and then there's going to be one column or one row. It's going to be solubility greater than 0.1 moles per liter, which is very soluble, and solubility less than 0.1 moles per liter, which is slightly soluble, or often referred to as insoluble, even though that's not 100% true. But anyways, if you're going to go across the top of your table to the ion, I'll just draw a little table for you down here if I can, just a rough sketch. It's going to have a couple columns, so maybe something like there's probably too many there, but I'll drop that, and then a couple rows. It's going to say ion, and then it's going to be solubility, less, greater, and these are going to be, the top is going to be the list of ions, so you might get like fluorine, and then like sodium, and so on, etc., etc., etc. And then you'll get something like most, and that'll mean most compounds with fluorine in it are soluble. Then you'll get the exceptions, like for example, lithium. So if you have a reaction and it makes lithium fluoride, you go over to your fluoride column, and then you go down to where lithium, or if lithium's there, or if it's in the most category. Well, lithium is mentioned as an exception. That means lithium fluoride is not soluble, and it makes a precipitate. So that means it's a precipitate product, and probably a double replacement reaction again. So yeah, a lot of information thrown at you. That's just how to read the table and how to use it, and what that has to do with double replacement. So the final driving force is the formation of non-ionic or covalent compounds from ionic reactants. So put covalent product. So that will be like gases a lot of the time. So like if you have ammonium, which is an ion, and ammonium reacts and dissociates, and it might lose the H minus, and it might make NH3, which is ammonia, and that is a covalent compound. And other ones that often occur are CO2 and SO2, and these are just like, they often come out in bubbles. You'll see when you're like in the lab doing it, or just gas forming in the equation, but they're usually covalent, and that means a double replacement is probably occurring. So again, I get it. A lot of information. I never learned this part when I was in class. Doesn't seem too important now, but this slide did teach you how to use the ionic or the solubility table and certain lab analysis techniques. So I wouldn't worry too much about the driving forces, but I would practice a lot with the solubility table. Alright, now the Barron's book is teaching single replacement reaction. So, much like the double replacement reaction where the two cations switched, in this reaction, the copper and the silver are also going to switch places. However, copper is 2+ in this case, and silver is 1+. So that's why you have 2 silver nitrate, because there needs to be 2 nitrates to cancel out the 2 copper, the copper 2+. So when we see the switch now, so the Ag is going to switch with the copper, single replacement. So we're going to have 2 Ag solid. Now see, in this ionic compound, the silver and the nitrate, the silver is a 1+, but it leaves its electrons behind, so or it trades them with the copper. Whereas the copper here had no charge originally, now it's copper 2+ because it's ionically bonding with the nitrate. So you get copper, NO3, 2. I don't know how to see there. Maybe I'll move it over a pinch. NO3, parenthesis 2. And there you go. Single replacement is fairly simple. And yeah, it's pretty simple. Just switch the metals, or the cations, I should say. Alright, well, net ionic equations are a huge part of the test. There will be a shorter answer section where they'll give you like a reaction in writing, and you'll have to turn the writing into a net ionic equation. So I should just explain what a net ionic equation. A net ionic equation is when all the ion pieces are separated. So if I'm doing the one before from the last slide where it's copper plus silver nitrate, instead of having silver nitrate together, you're going to have it separate. So it's going to be plus 2Ag plus 2 NO3 minus. It's going to yield. Remember, the copper and the Ag, their charges are changing. So copper is now 2+ plus 2Ag plus 2 NO3 minus. Now you see the NO3 minus didn't change at all. So in a net ionic equation, the NO3 minus is what you would call a spectator ion, which means it just didn't really do anything, it didn't really participate in this reaction. So the spectator ion is generally left out. So your net ionic equation will actually look like copper plus 2Ag turns to Cu2 plus 2Ag. Sorry, there's a plus there. That was my bad. Missed that guy. Alright. So that's what your net ionic will then look like. It's not too hard. You just need to separate ions from their ionic compounds and then move the charges around and then cut out the spectator ion. It's a little trickier for the net ionic reaction of double replacements because you usually have 1 or 2 spectator ions being the ones that don't change while the cations switch places, but it's not too difficult. Alright, well, the Barron's book also talks about redox in this chapter, which is standard reduction and reduction oxidation reactions. Now, that is another big part of your test, but it's also not really this unit. I feel it's a waste of time to explain it to you in a very basic way when just so you can understand more single and redox reactions. But if you want to learn about it right now, which I don't think you really need to, but if you're maybe further along in the year, check out Chapter 13. I'll put that down for you. Chapter 13. That is oxidation, reduction, reactions, and electrochemistry. So that'll be the chapter that I go over redox in depth on. So, alright, well, thanks for watching. It's Peervids Chapter 4.